Hello. Okay. We're gonna continue coming back to the original model of the what we call from the original paper of Band 6 in 1955, resorting to this type of LP model or linear. We call two-stage linear programming model. Okay. And last clip, we already show you an example how you can we implement this model to and under the platform of Microsoft Excel. And as you've seen from the last illustration that with a number of possible alternative happen in each uncertain parameter of the model can result to a very large scale of A and B, resulting to the additional variable of u and v, and the resulting model can be the size can keep growing, and until at one point that your computer will be facing out of memory or out of core, or maybe reaching some of the uncomfort zone that the response of the computational time is getting slower and slower. Okay. Today we're gonna start to show you a different way to solve this problem. Okay, and we will introduce you on the concept of what from this original paper way back in 1962. Okay, of J.F. Bender. The title of the paper we call the Partitioning Procedure, or in in other words, you can call there some decomposition instead of partitioning. Okay, and let's look at the model in the paper where they will consider to partition the set of decision variable to two type of x and y's. Okay, and with this generalization, that you can see that you can have a mix between linear and nonlinear model. Okay, f of y and capital F of y can be nonlinear function. Okay, and in some way, set of r's of p of x can be real and continuous, and set of capital S of y can be discrete data set. That's why they refer to 1.1 as solving what we call the mixed variable programming. Okay, because variable x and y can have totally have the same nature, can be both real or can be the mixed integer, like either one of them, x or y is integer, and the others, another one is continuous variable. Okay, this is not an easy paper to read. Okay, and I show you because it's the original paper way back. It was a paper first presented at the 8th meeting of management design in Brussels in 1961. And if you go back to the end of the papers, okay, let's move on to the last page of the paper. Okay, actually from the reference point, okay, you look at the reference number 2. Okay, actually, it was based on the thesis of Bender, okay, for a doctoral degree at Utrecht. Okay, that's one university in Germany. Okay, and many reference to a very classic. And Bill is also a very big name of computational LP. Okay, in England. Okay, and also Danzig himself, and Gas here. Gas is was a very first group of PhD students under Danzig supervision. Okay, you have Griffith, Stewart, and Goldman, Gomery. Okay, okay. This is a father of integer programming, one of the school of thought of integer programming called the cunning plane algorithm. Okay, Kelly is Ransondoy is another one, the branch and bound. Okay, for discrete optimization. Rosen also well-known nonlinear with his method, proposed method of gradient projection method. Sarit Alantakis, okay, and one of the founder of the classic KKT, Karash Tucker condition. Okay, and Susan Dix, okay, he's also well known about what we call the feasible direction method. So this is a way back, and historically many brand name of optimization person is in here. Okay, and as I told you before that we I will explain applying the resulting of this paper directly to the original paper that we work on instead of reading this paper in detail, just like what we go through Danzig's paper, okay, which have many example illustrated, okay. So we're gonna go here, okay, this is the direction here, okay. Uh, as you can see that we're gonna apply what we call the partitioning procedure or decomposition procedure, okay. You can see that there are two stage problem here. The first stage is the decision of x, as we already explained. Okay, and the second stage is the consequence stage. Is that after you make a decision of x, you get the resulting of u and v, and the resulting of u and v leading to the expected cost, linear cost of g transpose u plus h transpose v. Okay, so we're gonna separate. Uh, just like what Bender say, we have x and y. Our y going to be u and v, okay, all together, okay, and x is already x. So we're going to separate these two parts together. And when we apply the concept of Bender decomposition, okay, let's start with the first idea that we given a feasible x star. Okay, going back to the original model. Suppose that we set up some feasible solution of x star, replacing x with x star. With this kind of structure, you can know that x can be any value. Because once you substitute to the constraint here, except that x have to be non-negative. Okay, once x is non-negative, okay, a times x, no matter how the results of a times x come out, okay, either u or v can be feasible one thing to balance ax and b. If a times x is greater than b, okay, v have the value, okay, of that difference, and the positive value, okay. If a times x is less than b, then u have some value, okay. So no matter how, except that you can set up x as a non-negative value, the a times x plus u minus v equal to b is always feasible. Okay, so that's why we start with this. Okay, we given some initial variable of x star here, and once you have x star over here, okay, it c transpose x star become constant. Okay, so as a times x become a vector of constants. Okay, a times x star. So we can move them to the right hand side, and this one become a constant value. The remaining variable is only u and v, which is the trivial solution, right? The difference here, you can identify what is u and v become, and u and v always rely on a times x star. Okay, and based on duality theory, okay, you need to go back and review the concept of dual problem. Okay, every primal problem can be written in a dual form. Okay, and with this concept, when primal problem have a minimization of c, okay, the dual problem become the maximize of different function we call w. Okay, and the vector of the right hand side b minus ax star become the vector of the objective function. Okay, so and times what we call the dual variable we call y. Okay, so b minus a times x star, okay, if you transpose this and multiply by a vector of y, okay, that become the objective function of the dual variable. But in the primal, you have a constant of c transpose x star, so In dual, that the same constant was added here. Okay, so P, this is the notation of problem P here, is the problem that we are interested. Why? We continue to see. Okay, and with the dual constraint is that with u, I times u minus I times v. Okay, so it will be not that difficult to see that the dual form have to be written in this just a bounded variable y. Because when y, since u and v is multiplied by identity matrix, so with the y for dual variable corresponding to each constraint, okay, so when y refer to uh, identity metric transpose, it's always equal to identity, and then when multiplied to y in dual form have to be less than or equal to g. That's why y less than or equal to g. The same of y, but this time you multiply minus y less than or equal to h. In other words, when you change sign of the inequality, you get y greater than or equal to minus h. So this is the way we transform based on the duality laws, that we can write a dual variable here. Why we write the primal and dual in this form? Okay, as I told you, the primal is trivial to solve. So is the dual. Okay, the dual variable you see here is that you check the vector b minus a times x star. If the element in the vector is positive, therefore this is that positive value is a coefficient in the objective function multiplied to their corresponding y. And you want to maximize the w. So it is trivial to say that you just pick y at their upper limit. By pick the y value at their upper limit corresponding to the element that b minus ax star is greater or equal to 0. Okay, when it's equal to 0, it's either 1, doesn't matter, because this is a 0 coefficient. Okay, but when b minus a times x star is negative, okay, if it's negative and you want to maximize w, so it's trivial to say that y you want to pick the lower limit. Okay, because it's negative, you want to make it the least negative as possible. So if this is negative, so y we pick the most negative value or the lower limit of y. Okay, and as you know, c transpose x star is a constant. So this dual problem is also a trivial to solve. Okay, but why we solve this dual variable for? Okay, you have to understand that we still don't know whether x star is the optimal solution or not. But we know that once you get a feasible solution in the primal, okay, you can always solve the dual problem trivially. You don't need any LP code or software to solve it. You just check you just check the coefficient of b minus ax star. Okay, so how can we find the next x star, or be able to prove that now my current x is the optimal solution? Again, we're going back and try to utilize what we call the weak duality condition. Okay, for what is a weak duality? Okay, the weak duality say that let's consider the objective of both primal and dual form here. When the primal problem we want to minimize c, okay, and the dual problem you want to maximize w. You know, the weak duality always say that z have to be greater than or equal to w for all y. Okay, for all possible value of y. You know that all possible value of y can be determined from identifying the corresponding x star. Okay, So it become like a infinite number of constraints because you know that how many possible x can be infinite number of solutions that lead to the infinite corresponding y star, the optimum of y. Okay, so the inequality say that okay, c here okay greater than or equal to w. Why? Because the only point that both of these values can be equal is what we call the optimal condition, okay, for linear programming. Yes, you know that at the optimal solution of linear programming, C must be equal to W, which means when you want to minimize C, when C reach the minimum value, W reach the maximum value. They touch each other, okay? But beyond that, for each X in the primer, for corresponding with the same corresponding Y in the dual, C have to be greater than W, okay? For all Y here, for all. So this is the key application of the Bender decomposition, okay? So we now can develop what we call the iterative routine to solve this type of problem, okay? We're going back to see that. We're gonna change this C here to the new variable we call T, okay? Okay. We're gonna solve this as a problem, okay, for the new X, okay? Because you know that, okay, for y star here, b minus a times x transpose y plus c transpose x, for all possible y, based on the weak duality condition, c have to be greater than or w, okay? But that's for all y, for all possible y, which can be infinite number of constraints. But over here, we're going to say that, okay, suppose we start with x. We know x over here for this problem. We'll be able to find the y. And once you know the y, in order to find the new x, we're going to use this formula, okay? For the new x, suppose you have only one y, you just put it in this inequalities. And the reason we replace t to z is because in this T, you say that for all y star. But in the original Bender decomposition, Z have to be weak duality condition. Z have to be greater than or W for all y, for all y. But this one is only for all possible y star, and y star is corresponding to the x star that you first initiate. So this one become in order to find an improved Z value and to reach the optimal solution, we try to solve this problem as iterative. With the new x, you get the new y. And when you get the new y, you solve this problem to get the new x. Why you want to solve this problem? Because you know that this inequality is always true. Okay? And once you get the new x, you can go back and replace another x star here. Replace the new x over here in the x star, and then you get the new x y star. And once you get the y star, you add the new constraint. Remember that you add the new constraint. You do not replace the old one. Why? Because this one for all y star. And also the original of weak duality is that c have to be greater than or equal to the w for all y. For all y. So this one become like equation that have been added uh, times and times again. For the new x, you get the new y. Once you get the new y, you get the new. We call this a Bender cut. Okay, cut means equation that trying to cut the number of feasible solution and also try to improve the value of t. Once you keep adding this constraint, the t value will keep going up because you want to minimize t. When you add more constraint, t will be getting worse. Instead of you get minimum, the minimum keep getting higher. But you know that once the t here reach what we call the best of z that you found for each x star that you find. So for each iteration, you got to get the new x star here. And once you get the new x star, you can evaluate the Z, the real objective function, and pick the best one. It doesn't mean that in every iteration, in every round of improvement, certainly the T will keep getting higher, higher, higher. But C can be fluctuate. They can be going up, going down, going up. But you want to keep the best. The best is the minimum value of C. Okay? We're going to call that the upper bound. Is the C cannot be exceed the current minimum C that we found based on the X star. And also we're going to call T is as the lower bound. The lower bound is that it's going to keep the minimum value not going to be less than T. But the T is going to keep going up, the value of T keep going up because of the additional constraint in every round of improvement of T, right? Okay, so the process repeat by solving this one, the P problem, and then you get the new X star generated, and then with the new X star you generate a new cut here. You find the Y star, and this is the new cut. Okay, this is we can refer this model as a Q model. Okay, you solve the Q model, you get a stronger lower bound T, which means that T keep higher, keep getting higher, higher. And the process stops when the best solution found in P is equal to the minimum T on solving Q, which means that they reach the strong duality condition. Okay, so this is a very simple explanation based on the whole idea of Bender decomposition. But as I told you before, the original paper of Bender was written in a very general sense of because it can be the mix between linear and nonlinear, mix between the discrete space and continuous space. But we just apply them in this moment just for the both partition variable in two parts. It's a continuous variable, both of them. Okay, as you can see that with this decomposition, the benefit that you're going to get is that every time you don't need any computer software to solve for Y. It's a trivial solution. And once you erase finding the U and V variable, you're going back to solve for only the original X here, based on this Q model here. Okay, so if you look at the original model when we solve, and remember that from the last clip that we used the Microsoft Excel and OpenSolver to solve it. You need OpenSolver because with the a huge amount of additional variable of U and V based on the enumeration of all possible uncertain parameters arise in formulating the A matrix and the B matrix. Okay, and the B vector, sorry. Okay, so in this one, okay, you can see that in every iteration we only solve for X, no U and V. Because once you get the new X, you already been found U and V automatically. You don't need any software to solve here. You only need software to solve this routine again and again and again. Okay, so in the next slide, we're gonna go back to the Excel file from the last clip that we use the direct software and we need OpenSolver to use it because the total number of variables become more than 10,000 variables, 10,000 constraints, as you might remember. Okay, and in the real world with so many uncertain parameters, and if you were able to discretize it to make it a finite number of alternatives for each parameter, the total overall combination can always lead the linear programming to become an out of core or the very large LP that your current computing machine cannot handle it directly. Okay, so in the next slide we will illustrate that example and apply this concept of Bender decomposition to solve it. Okay, from now, okay, let's move to the next clip. Thank you.